I want to thank you all for coming to our 21st lecture of the Phyllis and George Halburn Radio Astronomy Lecture Series. We are extremely grateful to the Halburn family for their support of this series over the last several years. The chair of the department also has made it possible to videotape all these lectures. So in fact, all 20 lectures have been recorded, and you can see it online. Today, it's a great pleasure for me to introduce Shep Doeleman, who's visiting us today. Shep is a director of the Event Horizon Telescope collaboration that recently announced the sort of the best or the first ever image of a black hole. This remarkable achievement, capturing this image was a remarkable achievement, and he's going to talk about this achievement and also how they were able to really push the instrumentation to do submillimeter interferometry, and also the results from the image and the measurements that they've done, and future direction of the mission. A little bit about him. He received his bachelor's from Reed College in 1986, and then he went to MIT. He got his PhD in 1995. He was a postdoc at MIT for a couple of years, and then he became assistant director of the Haystack Observatory, which is actually run by MIT. And then in 2012, he moved to Harvard, and he's been there since. He, in fact, did some atmospheric experiments at McMurdo Station, South Pole, and Antarctica also. Antarctica, okay, so I have to say it properly. And also, he has, he's a Guggenheim Fellow. He was a Guggenheim Fellow in 2012 and spent a year at Max Planck Institute for Radio Astronomy. His group actually won the Breakthrough Prize, which was recently announced. And he's currently a senior research fellow at Harvard and co-leader of Harvard's recently established Black Hole Initiative. So let's just have a round of applause for Shep before he starts. So please also stick around because we'll have pizza at the end of the hour. Take it away.
Thank you very much, Farhad. I usually get the applause after I talk, so I'll be going now. Now that we've done away with the applause. It's a real pleasure to be here for a number of reasons. One is that for many years I was giving talks about what we might see with the Event Horizon Telescope, and now I have the privilege of being able to describe for you what we actually saw. And also, Fred is, of course, here, Fred Razio, and he helped us usher the first publications of the EHT into existence through AppJ Letters. So I want to give a shout out to AppJ Letters for making that possible and making it such a nice experience. So I am going to talk about the Event Horizon Telescope, how we imaged a black hole. I'm not the director anymore, I'm the founding director. They've elevated me to Olympus somehow. And I'm showing these results on behalf of the EHT collaboration. I'll give my spin on it, but the results themselves really are from the entire collaboration. It takes a global team to build a global telescope, and that's what we did. So the idea of the Event Horizon Telescope has been a long time coming. I'll describe for you that it has its underpinnings at the turn of the 19th century, or the 20th century. And there were some simulations that describe what we might see if we could zoom in to the environment right around a black hole. And then the art of making it happen really was an instrumental and observational one. And that's what I want to describe to you today and some of the results of that. But the idea was motivated by the fact that we could see a black hole for the first time. We could test Einstein's theories of the black hole boundary and understand how black holes energize the centers of galaxies. And if we could do that, we'd be tackling one of the central mysteries of astronomy and really physics. So I'm going to start off, as I do sometimes, by showing you the Hercules A galaxy, shown here. This is about 2 billion light years away, and at the center of this tufty optical image here is a black hole that weighs about 4.5 billion times what our sun does. But it really becomes interesting when you look at it in the radio. This is a well-known, iconic image that shows these light speed jets coming from the very center of the galaxy. Now, this is a moment that knocks your socks off, right? I mean, it really should. It never fails to amaze me that there is a powerful engine at the center of this galaxy that is driving these outflows that stretch 1.5 million light years across. And the only thing that we can think of that can do that is accretion onto a supermassive black hole, reprocessing that energy into these directed outflows. These lobes, this jet contains about 20 billion times what a supernova would output in one of its explosions. So if we could zoom in by many, many orders of magnitude, what would we see? Well, Jean-Pierre Luminet, in kind of some groundbreaking simulations in the late 70s, showed us that if you had a disk of material orbiting a black hole, a pancake of material orbiting around the black hole, you'd wind up seeing this shadow feature. And this was first derived theoretically by Bardeen in 1973. And the diameter of this shadow, through all this ray tracing, is about the square root of 27 times the Schwarzschild radius. And the Schwarzschild radius is the point, of course, where gravity is so strong that even light cannot escape from this black hole. And if the black hole is maximally spinning, if it's spinning as fast as it possibly can, then that changes to about 9/2 times the Schwarzschild radius. So this is quite interesting. This means that if you could take a ruler and lay it across one of these images, you'd be able to describe whether Einstein's theory of gravity was accurate at the black hole boundary. And a number of other groups, Falke, Takahashi, Broderick and Loeb and others, have described what these look like and how you can extract science from these images. What I love to show at this point is the first simulation that moves by Jean-Pierre Luminet. He hand-painted these dots on Canson negative paper using India ink, and then he animated it in 1979. And it turns out that all the features you see here, the last photon orbit, which is this thin line right here, the movement around this black hole, he captured pretty much perfectly. And so when you have an early kind of simulation, an early computer, you can do amazing things. And then, of course, with the modern computational fabric available to astronomers and physicists everywhere, many different groups have now simulated this. And you all wind up seeing this last photon orbit, this circular feature here, whether you use a schematic model here, as Broderick and Loeb have, or the Arizona group does here. You see GR-MHD simulations, or Monica Majobrovska does here. You wind up seeing this circular feature, which is the last photon orbit. That's where light orbits the black hole. It's essentially the impact parameter of this black hole. In all of these, you'll see an asymmetry, which will be important later. That's because the gas is coming towards you at near light speed. And when that happens, the emission gets beamed towards you. It's a relativistic effect. So on the left-hand side here, the emission is coming towards you. On the right-hand side, it's going away from you. And you see that basic asymmetric brightening everywhere. And most of the emission you see here is all radio. It's all synchrotron emission, relativistic charged particles moving around magnetic fields. So that's what you should be thinking. This is shining brightly in the radio spectrum. Now, how do we get this shadow geometry? This is an animation that we've created to kind of show you this. So you have the black hole here shown in red, and some of the light rays are bent gently around the black hole. Some of them do complete loop-to-loops. But if you were to illuminate the black hole from behind, and you were to situate yourself on the Earth, essentially at a distant screen, then you'd wind up seeing that impact parameter caused by the light bending around the black hole. And the last photon orbit forms the innermost boundary of that ring. And this is, of course, the square root of 27 times the Schwarzschild radius. Now, this goes back a ways. I found this paper by Hilbert in 1916, and there's that factor of the square root of 27. Not to be outdone, Max von Laue also showed that here in 1921. So people have been thinking about what a black hole might look like for a long, long time. So in that sense, this has been a delayed gratification process for over about 100 years. Now, the other thing I want to point out is that that's how light moves around the black hole, or how light is bent around the black hole. But matter moves in a very separate way, because matter cannot move at the speed of light. So if you have a zero-spin black hole here and matter is orbiting the black hole, then you wind up with an innermost stable circular orbit interior to which matter would just ballistically fall onto the black hole. If you have a retrograde black hole, you're orbiting in the opposite sense of the spin of the black hole, then you're constrained to orbit very, very far away from the black hole. And if you have a prograde orbit, if you're orbiting in the same sense as the black hole spin, you can sidle up right close to the event horizon itself. And the dynamical range here is about a factor of 10 to 1. So even though the light lensing does not change by more than about 10% from the high spin case to the low spin case, it's the dynamics that change dramatically for matter orbiting the black hole. And you can see here that the size of the ISCO changes as a function of spin. More importantly, the period of motion around that orbit changes from about 4 minutes for Sagittarius star, the supermassive black hole in the center of our galaxy, to an hour for a retrograde orbit. And for M87, which is about a factor of 1,000 times more massive, then these same numbers are days instead of minutes. It goes from 4 days to about 2 months. So it really does change in terms of the time scales. Now, the first and best evidence we have for there being a supermassive black hole that we could resolve is our galactic center. You can see here streams of a hot ionized material streaming to the center of our own Milky Way galaxy. And this white spot here is what we think traces a 4 million solar mass black hole called Sagittarius A star. The shadow diameter would be about 50 micro arc seconds, equivalent to seeing a grapefruit on the moon. And you can see these wonderful orbits of stars that have been made by the Keck group in UCLA and also Reinhard Genzel's group in Germany. These orbits are really amazing. I mean, they show that something is tossing around stars like planets at the center of our own Milky Way galaxy. Now, the problem is, how do you image something that's 50 micro arc seconds across? That's stretching the limits of what we can do with astrometric and astronomy techniques. So for Sagittarius A star, it really is an amazing opportunity. It turns out that that shadow size is about what you would require, is equal to what you get when you have 1 millimeter wavelength light coming from near the black hole and you have an Earth-sized telescope. Now, why is 1.3 millimeters a magical wavelength? That's a wavelength that is born close to the black hole horizon. It can go through the hot gas that's accreting onto the black hole, through intergalactic medium to the telescopes on the Earth, through the Earth's atmosphere. It's the one wavelength that can make that trip unimpeded. And the wavelength of light is related to the angular size of the features you can see on the sky by lambda over d, and that is less than the shadow size. So we can do this from the Earth. The Earth's atmosphere is turbulent, but the opacity is less than 1, so the wavelength of light can pass through the Earth's atmosphere without a problem. It turns out that the biggest problem to see Sagittarius A star is the interstellar scattering. There's free electrons between us and the galactic center, which causes even a point source at the galactic center to appear fuzzy. It's like looking at the galactic center through shower glass. So as a function of wavelength, the size that people were getting over many, many years, from the 1970s to the 1990s, followed that lambda squared law, that solid curve here, showing that we couldn't tell what size Sagittarius A star was. It was only when we got to 1 millimeter here in the late 2000s that we began to see the intrinsic structure of Sagittarius star emerge from the scattering. Okay, so all of a sudden we were not scattering dominated anymore. We could see the intrinsic size. And that was about the size of the shadow. This is the moment when we realized we could image the shadow of the black hole. And what was nice, of course, is that most of the emission from Sagittarius A star is peaking here in the submillimeter. So it's very, very bright, right around 230 gigahertz, which is 1.3 millimeters. So we have the right wavelength, we have the right object, we have the right setup so that we can start to do this. The big problem was the sensitivity. We needed to overcome the fact that at these short wavelengths, the dishes tend to be small, and they have to be smooth. It's very difficult to make a large, smooth dish. So we needed to overcome the fact that we had small dishes by digesting larger and larger bandwidths. And that's how we overcame the sensitivity problem. So the first inkling that we had that we could do this did come in 2008. And we used 3 stations in a very long baseline interferometer array with California, Arizona, and Hawaii, 3 stations. Now, on the short baseline, lambda over d the resolution of our interferometer is pretty poor. So we can see most of the energy from the black hole. So you'd expect on a graph of baseline length versus correlated energy to see most of the energy from Sagittarius A star, and indeed we did. So everything was as expected. On the long baseline, though, lambda over d gets smaller and smaller and smaller. So if there was a finite size to Sagittarius A star, you would be excluding some of the energy that the interferometer would see. And that's exactly what we saw here. On the long baselines between Arizona and Hawaii, we saw a greatly reduced amount of correlated flux density. And from this, we were able to get a size of Sagittarius A star, which was about 3.7 Schwarzschild radii. So right in the window where we'd expect to see the sizes of the shadow. Now, we did the same thing for M87. M87 is a completely different beast. So it has a jet, a relativistic jet, just like the one from Hercules A that you saw before. This is where the black hole is, and this is a wonderful animation from VLBI data from Craig Walker and his collaborators. We used the same setup as before, and again, we saw the same kind of resolution effects. And this time we got to 40 microarc seconds, which was about 5.5 Schwarzschild radii. So now we had two different sources that we could attempt to image with the Event Horizon Telescope. So let's look at M87 because it's probably clear to everyone. So everyone has seen the image, so we did image M87. So let's focus on that. It was first observed by Curtis in 1918, this little jet here. Now, you might ask, why is M87 called M87? Well, it's the 87th element of the Messier catalog. Messier famously did not really care about galaxies. He was a comet hunter. So the whole M list are things not to look at if you want to look at comets. So these were all the trash sources that he did not want to observe at all. And this is the 87th one of them. But you can see this optical jet here. And if you rotate and you zoom in, and you look at it also in the radio, you see they overlay perfectly. But what you also see in the radio here, this is a VLA observation at 20 centimeter wavelength, is this other bow shock here. So you get a one-sided jet coming out here, which impinges in the intergalactic medium here. So you see this shock, and you see an unseen jet doing the same thing over here. And this is, again, that Doppler boosting effect that I told you about before. This jet is coming almost directly at us, only offset by 17 degrees. The one on this side is moving away from us, only offset by 17 degrees. And it's Doppler deboosted to the point where we don't really see it until it hits that intergalactic medium. So moving in even more, with a very large array at 2 centimeters, we see this self-similar jet. The very long baseline array at 15 gigahertz, now we're at 12 light-year range here, keeps showing this very well collimated jet. At 4 light years, at 43 gigahertz, we're still seeing this core jet morphology. And this, up until recently, was the best image we had of M87. This is 3 millimeters with a global millimeter VLBI array, about a third of a light year across. And you can see here the edge-brightened jet. And the question is, what was in here? And this is what we found. This is 4 light days across. Our entire solar system fits 3 times over in this patch here. This is the best evidence that we have for the existence of supermassive black holes. What this shows us is that there is a compact object here that weighs 6.5 billion times what our sun does. It's within its own photon orbit. So from a GR perspective, this does look exactly like what we would expect a black hole to look like. Even more, you see that asymmetry which we expected from decades of general relativistic magnetohydrodynamic simulations, showing that there are light speed motions of gas around the black hole. These are coming towards us, and this is going away from us. This then also provides us with a laboratory to further explore strong field GR and how black holes operate in the centers of galaxies. So I'm going to tell you a little bit more about how we analyzed this data, how we made these images. So we use this technique, short wavelength VLBI. I think that in this lecture series, a few people have already talked to you about what VLBI is. I'm going to give you the short course here. We look at plane waves from the black hole, the radio waves from this distant object. We record them at radio telescopes. We use hydrogen maser clocks that only lose about 1 second every 10 million years to timestamp all of the data that's coming in. And then we record them on hard disk drives. And nothing beats the bandwidth of a 747 packed with hard disk drives. So we just send them back with FedEx. We have not lost any data yet, although we did have a mix-up once. It turned out that we got a bunch of boxes at the Max Planck Institute where we processed some of the data. They had bolts of fabric. And somebody in a fabric warehouse got a bunch of disk drives, and we got a bunch of fabric. We were able to swap. They were happy, and we were happy. Everything worked out well. But we do get mix-ups, but thankfully we can track them. And the idea here is that by cross-correlating the signals from these two radio telescopes at a central location here, you can recover a data set that's equivalent to having a telescope as large as the distance between these dishes. Now, if we only had two dishes, that would be a problem because we wouldn't have enough of a filled aperture to make an image. We might be able to make a size, as we did earlier, but we can't make a full image reconstruction. And thankfully, the Earth rotates, and we have multiple dishes. So what this shows here is all the dishes that we have in the Event Horizon Telescope, and each baseline here connecting two stations is one point here on this virtual aperture. And as the Earth rotates, we sweep out these curves over a night of observing, and we fill in enough of the virtual aperture that we can then make an image. Essentially, each baseline pair gives you a spatial frequency or a Fourier component of the image, because you can decompose any astronomical image into a bunch of sines and cosines. And two antennas pluck one of those components out of the sky. So when you get enough of them, you can reconstruct the image. So this is the array that we built out. This took us well over a decade in order to do this. So a lot of these stations were not designed to do VLBI. They were existing telescopes, amazing radio facilities in their own right, but they had not been built with VLBI in mind. So we had to bring to each of these sites an atomic clock, to each of these sites a high-speed digital recorder, to each site a bunch of electronics that would allow us to record the radio waves at high speeds. So we have the SMT here in Arizona, the LMT in Mexico, two telescopes in Hawaii, SMA and JCMT. In Chile, we have the OPEX telescope and, of course, the ALMA array. South Pole got into the game here, and our European colleagues brought along the IRAM 30 meter to observe with us. Now, as I said before, one of the key things about this was the instrumentation. I'm an instrumentalist. I like to think of myself as kind of a plumber, going to these telescopes and wiring in things and making sure bits from there get over to bits over here. And but we had to use mostly smaller dishes because they had to be smooth, and again, it's hard to make a big, smooth dish. So we developed this bespoke system here that's digested 64 gigabits per second. Now, to put that in perspective, the VLBA, which is a national facility instrument, records 2 gigabits per second. So we needed to think broadly about how to revolutionize the back ends for VLBI in order to pull this off. And what I love showing here is the fact that we've tracked Moore's law over 2 decades. I can't impress upon you how rare this is, that astronomers can track Moore's law for so long, right? So this is the recording rate of VLBI systems starting in 2000 going to 2020. And when we started doing the EHT work, detecting Sagittarius Star horizon structure and M87 horizon structure, we were down here about 4 gigabits per second. Now we routinely record at 64 gigabits per second. This blue line is a 18-month doubling every single 18 months. So with that, we were able to put these systems all around the world, and that really was the magic and the secret sauce that allowed us to make these EHT observations.
So what's the bandwidth of individual instruments, the receivers? What's the bandwidth?
So Farhad is asking what is the bandwidth of the receivers. Those are typically 4 to 8 gigahertz. So that's a very important point. We matched our digital systems to the full analog bandwidth of the receivers. Until then, we'd been leaving a lot of bandwidth on the table. So what the EHT did was they said, what is the maximum bandwidth we can get from ALMA or the best superconducting junctions in the cameras at the different telescopes, and we matched that. So we didn't leave anything on the table. We maximized our sensitivity. So a lot of things had to happen in order to expand this array, and this is what consumed me and others for a long time. We first got the large millimeter telescope in Mexico working. This is one of our graduate students, Gisela Ortiz, in Mexico, and she is adjusting the atomic clock. And this is the LMT here. It's a 50-meter diameter dish, so an absolutely essential component of the EHT. The OPEX telescope near the ALMA array got in on the game, and we used that to get our first detection to the South Pole, and this shows it here. So when you cross-correlate the data from the two sites, you wind up getting a peak in cross-correlation, and that's what's shown here in the red. This was our first detection to the South Pole. And then the IRAM 30-meter also got detections to the ALMA array. And then a few words specifically about ALMA. ALMA was the biggest technical lift that we carried for this whole project. And it was really the sine qua non. Without this, I don't think we would have been able to do it. ALMA, when you phase up all 60 dishes in ALMA, it's the equivalent of about an 85-meter diameter dish. And in addition to the bandwidth, we needed that extra collecting area in order to get the boost in sensitivity to make these images. So we had an international collaboration that was totally separate from the EHT international collaboration just to build this. And what we wound up doing is changing the internal correlator structure at ALMA. And believe me, it's really hard to get ALMA's permission to mess around in the inner sanctum of their instrumentation. So we went into the holiest of holies. We went into the correlator room, and they let us reach into it and mess about with it. And this only happened because we came up with a very robust design, got approval from the ALMA board, got funding from the National Science Foundation and international groups, and then went through a very rigorous process of reviews in order to do this. And what you can see here in the upper right.
And I'm sorry.
Oh, yeah.
So when you made these changes, were these permanent changes you were making?
Yes. Yeah, so these are permanent changes.
ALMA had to live with that. Did it benefit other science that you had to make that?
Yeah, that's what a wonderful question. That's a perfect question. It turns out that when you phase up ALMA, you're essentially in real time doing adaptive optics. So you get a pencil beam equivalent to the resolution of the whole array that is in real time being phased up. And that's wonderful for pulsar work, for example. So there's a lot of other science that benefits from having this particular capability. Now for us, we use it for VLBI, but there are other cases that they can use it for. So they wanted to leave it there. Yeah, so these are permanent changes to the correlator. And what you wind up seeing here is that before you turn on the system, the phasing of all the different telescopes, the phase offsets, are essentially random. So they're not phased together. And when you turn on the system, the mean RMS of the phasing reduces down to about 9 degrees. So almost near perfect phasing. We routinely get better than 90% phasing efficiency, grouping all the ALMA dishes together. It is by far the most sensitive element in the Event Horizon Telescope array. So then that brings us to April 2017. This was the moment. All the telescopes in the EHT swiveled to look at the same objects at the same time, M87, Sagittarius A star. We had 60 hours of ALMA time, which is a lot. We had, for those of you who have observed with ALMA, it's a fair amount. We had an 8-station array, which you've seen already. We had a 10-day window, and we triggered 5 days out of that 10-day window. Why do you trigger 5 days? Because if it's snowing in one place and it's clear in another, you still don't run. So you need good weather at all the sites together. And so you play a kind of a game theory scenario to find out when you want to trigger these days. We did wind up getting fantastic weather, and we got detections to all 8 participating sites. Now, the ALMA phasing really comes into play here. I can't stress enough how important it was to have ALMA phased up for this. So it turns out that if you have a triangle of baselines, all with 3 different stations, here we have ALMA to Mexico, ALMA to Arizona, and then Mexico to Arizona. You see here the amplitude in blue and the phase in red. The phase is wildly variable, and that's because the atmosphere is delaying the signal to and from each of these sites, so it's changing on the time scale of minutes. When you do a round-robin sum, though, you can use the fact that you have very strong detections on the 2 ALMA baselines here. Every 1 second, you have so much signal-to-noise ratio that you can calibrate out the atmosphere Even though the atmosphere is trying to change the phasing of your entire array, you can take it out, and you wind up transferring all the phase noise here to this weak baseline. But even there, it's so high signal-to-noise ratio, you can coherently integrate. The reason this is important is that now you can build signal-to-noise ratio with the square root of time. So you can integrate for minutes and build signal. So even on a relatively weak baseline like this one, you can get a detection. And what that means is, I'll show you some examples about that. So this is an example of Mexico to the SMA, to Hawaii. You get a detection here before you use this phase compensation technique with ALMA. And then afterwards, you just get this beautiful, coherent detection. Okay? And this was really the key. When you use that, everything you see here, this is that virtual aperture that I showed you before when the Earth was rotating. Every point here is a detection. Every time we looked at M87 with the array, we got a detection. There were no cases where we did not see the source. And that's because we were able to build signal-to-noise ratio in a very robust way. So it maximized the filled aperture that we were able to use for imaging. Now, one of the hallmarks of the EHT was the fact that we didn't know what we were doing. Maybe that came out wrong. What I mean to say is that nobody had ever imaged a black hole before. Okay, so we didn't really have a template for how to do what we were doing. So we had to triple and double check everything. It wasn't enough for us to use the Haystack Observatory processing system, which is how we found fringes, how we did the detection process. We also compared it to the ALMA standard CASA pipeline. And we also compared it to the legacy APES pipeline. We ran all of our data through 3 completely independent and separate pipelines. And then we looked at the histograms and compared them all to ensure that statistically we were seeing the same thing. At every stage, we used this creative tension amongst the collaboration in order to check our results. And this is an interesting cultural phenomenon. This was not a cage match. We did not make it adversarial. We did not say, if your pipeline gives us the best results, we will then not use the other ones. Everything went in the papers because it was very important for us to verify each pipeline against the other one. And that created this culture of willingness of everyone to pitch in, even if their final data pipeline was not theirs, because everybody got mentioned in the paper, everybody provided the vetting that was required to make this a robust process. Now, this is the first inkling that we had something interesting. Okay, so before I showed these basic plots before, this is energy on a various baseline, and this is baseline length. I had only shown you the first part of this curve before. But now we had such long baseline coverage and such good sensitivity, we could see these bounces that we had never seen before. And to those of you who can do Fourier transforms in your head, what you should be thinking here is like, this is a ring. This dotted line here shows the Fourier transform of a ring that would show up on this kind of plot with data here. And we know this was a ring and not a filled disk, which also gives you kind of the same basic structure, because a filled disk would have a second null here instead of here. So right away we were thinking, this is looking pretty ring-like. But again, we didn't really know what we were doing. We hadn't done this before, so we split ourselves up into 4 completely separate teams. We had one team here was mostly in the Americas. Team 2 was more of a global one, focusing on MIT and Europe. Team 3 was Europe and also Boston University. And then Team 4 was mostly the East Asian group. And each used different techniques in order to image the black hole. And I'll go into that a little bit. And the important thing here was to assess human bias. We wanted to have 4 separate teams so that we didn't have groupthink. And when I say groupthink, what I mean is that we really wanted to get all these different teams with completely independent views on things. This is Team 1, Team 2, Team 3, and Team 4. Team 3 is very happy here. I don't know why, when that was taken. But I also want to stress that we reached out across the entire collaboration. This was really a collaborative effort. And when we all came together to compare results, it was a very uplifting moment. You get a little bit emotional thinking about this. When we all came together It was a lot of camaraderie when we all looked at these images together. Now, the reason we do this is, of course, because labradoodles look a lot like fried chicken. And this is what I mean by groupthink. We did not want everybody getting into a room together thinking that they were looking at fried chicken when they were actually looking at labradoodles, because then you wind up really focusing on fried chicken or labradoodles. And of course, I like to show this one too. Chihuahuas and muffins are just virtually impossible to distinguish. Okay, so there was really a reason for this, because we really wanted to make sure that we were looking at something that was real and robust. And this is what happened. So we all got together at the Black Hole Initiative at Harvard University in July. I had just come back from a trip to Europe just in time for this. And all 4 teams showed these results. And this is really when we began to think that we were onto something. We had hints before, but this was the moment when we felt that there was possibility of seeing that last photon orbit. And here we are at the moment when we're deciding on a consensus image. And what's important also about this figure, this photo, is that there are as many people on a speakerphone as there are in this picture. Okay, so we drew from every part of the collaboration. Everyone was able to enjoy this moment virtually if they weren't here in person. Now, we weren't very satisfied with that, of course. We spent a long time. In fact, we put them, yeah.
I was going to go back to the 4 teams. You talked about the 3 software packages, APES, CASA, and the other one from Haystack. Do those 3 packages map in any way to the 4 teams?
So it turns out that roughly they did. So we had, although those were data processing packages, we had 3 separate imaging packages too. So really, we had 4 teams that broke down along the lines of traditional clean algorithms, which are the ones that you'd see in APES or in CASA. And then there were 2 maximum entropy methods that were new, tailored, and kind of bespoke for the EHT. And those were compared against the clean algorithms. And ultimately, those gave better angular resolution than the clean algorithms, but we blurred them to match the clean algorithms to be maximally conservative. So we think we can actually do better than clean, but for the moment, we are just saying we're doing at least as well as clean, and clean clearly shows that ring. Does that make sense? And people used multiple methods. The most important thing was that the 4 teams were independent, that they were not cross-fertilizing in any way. So what we did is then we said, okay, all these algorithms that we have, the clean algorithm, the maximum entropy algorithm, maybe we've tuned these to look for rings, right? Maybe like a child with a hammer, everything looks like a nail. So then we trained them specifically on things that were not rings, whole disks, for example, or doubles, which can give you that same ringing structure when you do the Fourier transform. And when we did, we looked at filled disks, we got filled disks. When we look at doubles, we got doubles. And we tuned these algorithms to look for non-ring structure. We optimized them to look for non-ring structure. And then we still found the rings. So that's when we began to feel that this was a very robust possibility. And these are the 3 different imaging packages. These are the final images for one of the days. We have a DiffMap, which is a clean algorithm, and then 2 maximum entropy algorithms. And they're giving basically the same structure. Now,
Can I ask
yeah.
a question? Were you doing analysis with simulated data before you collected data?
Absolutely, yeah. So this is a very good question. So we had imaging challenges, and we went through 5 rounds of imaging challenge. So over the course of about 18 months, we had 5 different challenges, and we would make synthetic data, which were corrupted with the known instrumental responses, and then we would feed them through all of these different packages, and then they were all blind, and then we would have a comparison afterwards with the truth image. And we refined all of these algorithms over a period of about 18 months. So they were routinely and robustly finding the truth structure.
And then did you run the methods after you ran on simulations and you optimized, as you said, for disks or rings or double? Did you then run them blind on your data, or did you have some let's say playground data from early data taking, maybe with bad weather or whatever, and then you ran frozen analysis on the actual data from the telescopes
Oh,
to get images, or
yeah.
did you keep optimizing and training the algorithms?
Well, so first we did an adversarial training,
Okay.
where we trained them on to look for things that were not rings.
Rings.
Okay, and then we put it back on the data in the sense that you're talking about, and said, now what do you see? And we still got those rings. But then, in a very interesting creative tension, we did exactly what you're talking about. We had 4 different days,
Okay.
and so we could take the settings that worked on one day and use it on the other days, right? And in a round robin sense. And then we had 2 different band passes. We had a high band pass and a low band pass that went through completely different instrumentation paths. And then we would use the settings for one on the settings for the other. And then we had different polarizations. So then we used the same on one polarization as on the other polarization. So in that sense, we jackknifed our data and looked in multiple different ways using the same settings. And this was a very robust result after we did that. That's exactly a wonderful question.
Yeah, I have a question.
Mhm.
Could you say more technically what it means to train an algorithm to not see rings?
So what we did is we trained it on a synthetic data set that we knew were not rings, so a filled disk, for example. And we trained it, so we went through a whole parameterization process, because there are many hyperparameters you can tune for the maximum entropy algorithm, for example. So you look at the priors. So what kind of priors are you using for maximum entropy? And what kind of minimization techniques are you using? And you tune these so that you are getting extremely good results for disks. And then you run it, as Vicky said, on the real data. And then instead of finding a disk, you get this nice ring forming. That's the sense in which we trained it on non-ring structures. This is a good crowd. Hopefully you've been thinking to yourself, yes, but do you always find rings? And the answer is no. When we look at core jet sources, like 3C279, for example, we see the kind of the canonical core jet source, and each one sees exactly the same kind of thing, which is kind of the structure one might expect from the longer wavelength images of this quasar. So each of the 3 different methods found that same structure. And then this is what I was saying before, we ran it on all the days, so each day is essentially an independent probe of this structure. Now you do see that the careful eye will show there is some change here. So you get this bright spot here moves a little bit down to the south. We think that's real, but we're still analyzing this from the standpoint of the robustness of these features. But so they are different, but we still get that same ring-like structure in each of these. And it's going to be the process of the coming decade for us to start making time-lapse movies of this source. Because GM over C cubed, or the light crossing time for M87, is about a day. So if we had 1 image a week, we'd be able to map motions around the horizon of M87. Okay, so how important are new sites? This will come up a little bit later. I've got to hurry up, I see here. So if you have only 2 sites here, you can tell the size of the emission. If you add another site here in Chile, well, you can tell that it's a little bit smaller. It's only when you start getting an outrigger site here, from a VLBI perspective, that you start to see a little bit of that ring structure. And only when you had all of the sites that could see M87 together, filling in the virtual aperture here, did you see the ring. So VLBI, as with real estate, is all about location, location, location. And that'll come up a little bit later when I talk about where we want to put our next dishes to sharpen our imaging even further. And then this is a little animation that was put together by Daniel Palumbo, Maciek Wielgus, and Michael Johnson, that shows how the data that's increased as a function of time goes into the imaging. So these are the 3 different imaging techniques, and you'll see here how we fill in the Earth aperture, and then how it gets plotted here. And you can see that when you have one baseline, you can't do too much, but as soon as you get another baseline, then the best images you can make begin to become a little bit more sophisticated. And finally, you begin to see this null structure here, and you can start getting very, very good ring-like structure as a function of time, and it keeps getting better until you start to lose the mutual visibility of your target.
So what's the dynamic range for these images?
So that's a great question. The interior null here is about a factor of 10 less bright than the brightest regions here on the ring. So we have about a 10-to-1 dynamic range between the null here and the ring structure there.
Sorry, I missed that. What was the difference between the three? Is it three different algorithms?
Yeah, these are three different algorithms being used, and at each stage we take just the amount of data cumulatively that we've had and make the best image that we can at that moment.
So I'm no imaging expert. 10 to 1 does not seem very high to me. What is?
Yes. So when I talk about the dynamic range of the middle here to the end there is about 10 to 1.
Yeah,
It's actually
in imaging, is that high for radio imaging, or is that?
Yes, so that's actually the ratio of the interior to the edge here, but dynamic range really is the color gradations across here. So I would say that the dynamic range here is closer to about 20, which is bad, Vicky. It's actually not too good, but it is enough. So yeah, I want to tell the difference between not optimal and sufficient. So and what's going to happen is in the future we're going to get more and more stations, which will make the imaging fidelity that much better.
Yeah. So what do you need? You need more stations for bigger contrast, or you need?
Yeah. So you're asking what is the rate limiting step? The rate limiting step is antenna placement. By far, the thing that we're missing most right now are new stations. So so in other words, we already have ALMA, which is effectively an 85-meter dish. Right, so we're not going to get another ALMA, right? But hopefully we will have smaller dishes around, which will fill in the virtual lens. I have to hurry here. So so then we had a whole theory wing of this project. We made 60,000 different general relativistic magnetohydrodynamic models to try to understand what we were seeing. Attention, this is seizure inducing. Okay. So it does move, and we parameterized all of these models with electron temperature, magnetic flux, black hole spin, all the things that normally characterize a GR-MHD simulation. This was put together by Avery Broderick, but there really was a large group of people that contributed to this. This was a major, major undertaking across the collaboration. And what we found is that there was only one way to really interpret this brightening in the south, and that was that the black hole is spinning in such a way that it is pointing into the page. And the reason is that when you have a spinning black hole, it tends to entrain the material that's falling onto it in a certain in the same sense as its spin. And even if you have a counter-rotating disk, when you get close to the black hole, the material that's emitting is still moving in the sense that the black hole is spinning. So the only possibilities here is that the black hole is pointing off to the left here in the direction of the jet that we don't see for M87. And here you're seeing a prograde orbit. So the black hole is spinning with the black arrow here, and the disk is moving in the same orientation. And you see that this is coming towards you, as you would expect. And here you have a counter-rotating disk, but the black hole is still rotating in the same direction, and the material is entrained to move with the black hole close to the event horizon. And that's the gas that you see emitting here that's coming around the bottom of the black hole. So we disfavor these, we favor these, and we have, for the first time, oriented a black hole spin in space relative to its relativistic jets. This just shows you what, a cartoon of what the accretion flow probably looks like around one of these things. And these then show that when you have a prograde disk, it's kind of hard to see here, but you can see the material spinning in here in the same direction as the yellow stuff here. When you get close to the black hole, the gas is spinning with the black hole. And here, even though the material is flowing in this direction, the black hole is spinning this way. Close in, this blue material is again moving with the black hole. So in all of these GR-MHD simulations, the material close to the black hole is spinning with the black hole. Now, then we weighed a black hole. So we had a whole separate section of the collaboration that was doing geometric modeling. And so you see something like this, and you say, well, can I model it? And it turns out that with relatively few steps, you can make some very, very nice models. This was put together by Dom Pesci, who was one of the masterminds of the modeling, along with the group at Perimeter Institute. And you can move that around, and then you can blur it. It starts to look a little like our image. And the important thing is that then you can, with a relatively small number of model parameters, do an MCMC process where you can really look at the histograms of all the different elements that go into this model, how big the black hole is, the width of the ring, and you wind up being able to peel off some uncertainties, in this case in diameter versus orientation. You can get the size of this black hole. Now here's the problem. We want to get the photon orbit. We think that we are seeing the photon orbit. We don't know if we're seeing the photon orbit. So we did the only thing that we could think of that made sense. We went back to all these 60,000 GR-MHD simulations, and we said, for each of these, we know exactly what the photon orbit is, because we know what the space-time is, we know what the mass is. We then performed a GR-MHD simulation. We generated synthetic data. We made a geometric fit, just as we did, just as I just showed you. And then we saw that we were not recovering the photon orbit. There was a difference. There was a scaling between what we recovered with the geometric fitting and the actual photon orbit. And we empirically found out from all these GR-MHD simulations what that factor was. And another way of showing it here is that we're after the shadow diameter. There's the square root of 27. We actually measure an angular diameter because we don't know how far away the black hole is, so we have to divide it by the distance. And so we have the square root of 27 times 2 times the apparent angular size of the gravitational diameter. And so basically we have a constant proportionality times this gravitational diameter. If it was maximally spinning, it would be 9.6. If it was Schwarzschild, it would be 10.4 for a pure photon ring. But here's the problem. When you look at these GR-MHD simulations, you see those wisps that are going around the black hole. So some of the emission is coming from outside the photon ring. Some of it's coming from inside the photon ring. So we asked ourselves, what was the empirical scaling? And we estimate that because we know what the photon orbit is after we make these simulations. And I'm running out of time a little bit here, but we looked at the error parameters by looking at 3 different instantiations of the noise through these GR-MHD simulations. And then we also looked at across all the different GR-MHD simulations we had, and we asked ourselves, what is that constant of proportionality? What do the simulations tell us is the relationship between the fitted ring and the actual photon ring? And the dominant source of uncertainty was all the different models. Okay, but even when you take all that into account, we're able to get this constant proportionality here, and we measure the mass of the black hole to be 6.4 billion solar masses to about 15%. Okay, so so there are some limits to this process. We've used these GR-MHD simulations in order to empirically calibrate. So we're assuming those GR-MHD simulations reflect reality. But when we do this, and looking at all the different uncertainties here, we do get a pretty robust estimate. And then we weren't content to do just this. We also used image domain feature extraction. So here, instead of using a model fit, we took that image and we measured the diameter of the image all around. We'll just cut to the chase here. And you measure the diameter and the uncertainty. And again, we were able to get that the apparent size of the gravitational the size as a function of technique and also on each of the separate days. And again, we found a mass of about 6.5 billion solar masses. So with 2 different techniques, we got the same answer. And then there was also a third one we fitted directly to GR-MHD models. Now, the interesting thing here is that we have these 3 different methods of measuring the mass of the black hole. Going into this, there were 2 values of M87's mass. One was based on gas dynamics around the center of the galaxy, and one was based on stellar dispersion, the motion of stars around the black hole. And all of our estimates are completely consistent with the stellar dispersion. So we think that this indicates that we resolved this outstanding problem of how you measure a black hole mass using other techniques. And we feel that the stellar dispersion method is probably better. So where are we going in the next couple of years? We're going to add these new stations. So Vicky was asking about what will help us most. What will help us most is adding stations to the array. We're going to work on M87 polarization. And of course, Sag Star. By far the biggest question, or the most frequent question I get is, where is Sag Star? And the answer is that GM over c cubed for Sagittarius A star is 9 seconds. The orbital frequency is about 4 minutes to half an hour. So the problem is that it's very difficult to make an image from one night of observation because it's moving while you're trying to make the image. So we have to adapt our techniques to dynamical imaging and make movies. And that's taking us a little bit longer than we thought. Magnetic fields, we think we can tell the difference between magnetically arrested disks and standard and normal evolution. For mad polarization ticks, we expect to see these nice coherent structures close to the event horizon because the magnetic field is being compressed and you get these azimuthal symmetries around the black hole. So as soon as we can make magnetic field maps, we hope to tell the difference between these two fundamental accretion modes around supermassive black holes. And then over the next decade, we're very fortunate to have just gotten a major grant from the National Science Foundation to build this out over the next decade to make movies of black holes. Phase 1 will be a design. Phase 2 will be build out. We want to add 10 to 20 new stations all over the planet. And the reason we can do this is because ALMA is so sensitive that even a 6 or 8 meter diameter dish can give you very good scientific data. So we can tailor locate all of these different dishes anywhere we want, most anywhere we want, in order to build out the Earth-sized aperture in an optimal way. We want to expand the bandwidth by a factor of 4, increase our range to 0.87 millimeters. Our data volumes are going to be insane. I mean, right now we record about 10 petabytes per campaign. We're going to be recording at least 100 petabytes. And we have to get all that data back, so we're thinking about free space optical transmission techniques using uplink to satellites and back down again. Data processing is going to increase by a factor of 16, and we hope to handle that by shifting all of our processing to the cloud. And then over the next 4 years, we'll be optimizing all of our algorithms and data pipelines to allow us to make movies instead of just still images. This is one instantiation of what it looks like. All the blue traces here are the new baselines that we'll get with the next generation EHT. And this is what the aperture coverage looks like. The black here is what we have now. The red is what you get at 230 gigahertz with new stations. And then if you add 345, you get the blue. So we are set to be able to make much higher fidelity images. This is what I mean by higher fidelity images. Right now, if we had a core here, the black hole and the jet, we could not really determine where the emission from the jet is coming from. So if you want to study jet launching, we can't do it currently with the EHT, but the next generation EHT can give us extremely high fidelity images of this jet, complete with bumps and wiggles. And that will be the key to unlocking the jet launching mechanism for these sources.
It's also 330.
What's that?
It's also 330.
Also 345. Yeah. And then, of course, we don't want to be bound by the dimensions of the Earth. If you had 4 Earth orbiting telescopes, look how fast you fill in the Earth-sized virtual telescope compared to what you would get when you have to wait for the Earth to rotate. This is going to be the key to making movies using low Earth orbit satellites, and we're looking at that right now. And then, of course, what kind of movies do we think we can make? So this is a GR-MHD simulation created by Andrew Shale, and then Maciek Vilgus, Daniel Palumbo, Michael Johnson, and Katie Bauman have shown what kind of movies we might be able to make with the current EHT, the kind of movies we can make with low Earth orbit satellites. And then if we also put a geosynchronous satellite up there, then we get enough angular resolution that we can start to make a movie that looks pretty much like this over here. So we think this is the kind of movie that we'll be able to make in the next decade. Imagine being able to see a real-time movie of Sagittarius A star. That's what we're after.
What's the time scale of these movies, and do you have enough time to accumulate signal-to-noise ratio to integrate for the image and see the time variation?
Yes. The answer is yes. I think yes, yes, and yes.
Okay.
Yeah. So it turns out that having ALMA allows even small Earth orbiting stations to be very viable. So even if you had a 4 to 6 meter diameter dish in space, having ALMA allows you to get 1 second or a few second detections to that site. And that's what allows you to fill in that lens, that virtual lens, which means that you have snapshot capability about every minute or so. And that's the key. And then I'm not going to spend too much time on this, but one of the nice things that Michael Johnson, Alex Lupsaska, and now theoretician Andy Strominger and a group of us are working on is looking at the very sharp ring, the very, very sharpest part of that inner photon ring. If you had a long baseline, maybe 1 trillion wavelengths out to the moon or L2, then this ringing you get becomes very pronounced, and you can see it all the way out to very long baselines because all the rest of the fluffy emission that comes from the unknown emission mechanisms around the black hole are resolved out. You're only left with the razor-sharp inner photon ring feature. And what you're seeing here is n equals 1 is light that goes 1 time around the black hole. N equals 2 is light that goes twice around the black hole. And n equals 3 is light that goes 3 times around the black hole. You lose a lot of intensity every time, but it gets sharper and sharper and sharper. And it looks as though if we went out to the L2 point, 1 million kilometers from Earth, we would probably still be able to resolve that out and see all the bumps and read the spin of the black hole off directly. And that's something to envision for the next decade and maybe even beyond. So I'm not going to read through all of this. I think you know kind of where we stand. We've made the first image of a black hole. We think it's the best evidence for the existence of supermassive black holes. We feel it's a new window that we can study these objects on in the future, both with getting better images, time domain, and possibly space expansion. This is our group. It's been a privilege, really, and an honor to work with all these people. We built this group up from a very small group, maybe 20 people in the early 2000s, to over 250 now, 60 institutes, 20 countries and regions. And I like to say that in this project we've jumped off cliffs and invented parachutes on the way down, and I can't think of a group I'd rather jump off a cliff with than all these guys. And then, you know, the impact on humanity, I guess that's for the history books to really decide. We were pretty much floored when we came down the day after the announcement and saw that it was on the front cover of every major newspaper in the world. We even got our little Google animation here. Like McDonald's, we feel we've served about 4.5 billion people. That's just an estimate. Your mileage may vary. But we think this is an uplifting story. It's one that I think has inspired a lot of people. And where we can, even though we're absolutely 100% scientists, we do need to make links to the broader community and the public where we can. And we'd like to investigate how we can do this in the future. So thank you very much.
Amazing stuff. Blows my mind just to imagine what you guys have been able to achieve. I was wondering, do we need to go through the image plane when we're comparing models to observations? Can you do it directly in the Fourier plane? Because there it seems like you will be less dependent on the imaging algorithms. You will compare directly what the models predict and what you observe one-to-one.
Yeah, it's a wonderful point. And the answer is absolutely yes. So all the modeling that I showed you, which was a whole tranche of analysis in our collaboration, was done fitting directly to the visibility plane. We didn't image at all. In my view, and I think the view of many people in the collaboration, they really are complementary. You want to be able to image in kind of a non-prescriptive way, maybe with a couple of priors, but not much, just to see what you're getting. And then if you want to really extract parameters, then those images can guide your model creation so that you get the bare minimum of parameters, so you can extract things like photon ring size and things like that, just fitting to the visibility data. So there are two different approaches, and we used both.
You have questions?
Yeah, just a clarifying thing. When you were talking about measuring the mass of the black hole, this d-star parameter came up that kind of tells you how curved the black hole is. But it seems to me that there should be a strong degeneracy between the black hole spin and the mass.
Yeah.
And really the mass measurement seemed a lot tighter than I would expect because I'm not sure how we can really break that degeneracy with the.
Yeah. So this is a great question. So when I said we had 60,000 GR-MHD simulations, that was marginalized over all spins. So we can't really say much about the spin of the M87 black hole at all. We have retrograde solutions. We have prograde solutions. Each fits the data, or can be made to fit the data equally well. Now, it turns out that because you're looking down, almost down the throat, 17 degrees off, the difference between all these spins is not much. There's only a 4% difference between the extremes of spin
As far as the light ring.
as far as the light ring goes. So this is exactly the question to ask. We've marginalized over all that, and that's built into the uncertainty. But we can't say much about the spin at all of the black hole. But it is almost entirely determined, though, by the mass.
Yeah, I was wondering if you could say more about the ALMA phasing project. So I'm familiar with the idea of phase closure, and I assume that ALMA did that before you came around. What is it in addition that you do? What's the idea of the ALMA phasing project that gives you better than what you get from just phase closure that you described?
Oh, do you mean the phasing or using the ALMA?
Well, the changes to the correlator that you made. I thought that was called ALMA phasing project.
Okay, so there are two elements of that. So one is, if we were going to use ALMA as a VLBI element and we didn't phase it up, we would need 60 different VLBI backends to record all of the different signals from all 60 dishes. So you have to phase it up in real time if you want to make one recording. So you only have one shot at coherently combining all those data streams in real time if you want to have one recorder at ALMA, if that's what you meant.
I think that's what I meant. It's the real time aspect.
It's the real time aspect.
They didn't have real time.
Yeah. So here's the cool thing. If you get an ALMA data set, after the fact, you can run self-cal, you can do all the imaging, and it will effectively phase up the array. But it's useless for VLBI because you have to record the bit-for-bit Nyquist sampled raw data stream after it's been combined. So what comes out of the correlator from ALMA, if you get a data set, is like a 16 millisecond dump time. And that's far too slow to do VLBI with. So you only have one shot at it. You have to phase it up in real time, if that makes sense.
I see why that would also help pulsars, because that's also a real
Exactly. So for pulsars, you want to have like 1 microsecond resolution in order to look at all the interpulse structure.
More questions? Yeah.
Thank you.
Hold on. So the mass you're getting, how does it compare to the mass we knew for M87 from previous?
So there were two.
The stellar and the gas.
Yeah. So it matches the stellar mass
Oh, that
perfectly.
was the band you
Yeah. So it matches
Okay.
the stellar. So it's the Gephardt mass. Carl Gephardt did that, and then Janelle Walsh has been working on the gas dynamics, and it appears as though all of our estimates are perfectly consistent with the stellar dispersion. Yeah.
Well, why is it not working for gas?
Well, I'm not an expert in gas dynamical estimates of black holes, but there are a lot of things that gas trace, the gas traces that stars don't. So gas can have pressure effects, it can have shocks. There are a lot of things that gas can do that can mask some of the actual dynamics of the
But
material.
also, they may not really rotate in the same rate either, because you could have basically kinematics of gas and stars be different.
Exactly.
So that's maybe the reason.
Yeah.
So I have one quick question also. You consider also adding the zero spacing to your data? Because in all of these are basically interferometric data.
Mhm.
So have you considered also adding a zero spacing?
Yeah. So we effectively do get that because we have the OPEX dish and the ALMA dish.
Okay.
They're only 5 kilometers apart.
Okay.
That's effectively a zero spacing. And then even closer, we have the SMA on Mauna Kea and the JCMT, and they're only 100 meters apart. So we effectively get zero spacing from those particular stations. And then we also, of course, use the ALMA array alone to look at the flux density as a function of time for Sagittarius star and M87. So we do factor all that in our calibration.
Okay.
yeah,
There's one other question. Yes.
So with so many methods and ways of showing that you can get things that are consistent with each other but slightly different, how do you choose which image ascends to fame and glory?
Yeah. What a wonderful
How
question.
do you choose without being killed by the
Yeah.
collaborators?
So it turns out that in some sense, we averaged some of these together. So the final image that we show is an admixture of these different techniques. And we did it in a way that reflected the uncertainty that we felt was real in all of these. So there's in the papers, we do go through a very careful analysis of which features we think are real, which features we think could be artifacts.
They get weighted a little more than
Yeah, exactly. Well, I think everything was pretty uniformly weighted in the final image that we showed. But we did, for example, we blurred the maximum entropy methods to be the same resolution as the clean algorithms, because we didn't feel like we had the justification to show the much finer resolution. And we think that with time, we'll be able to refine those techniques and make the claim that we can super resolve. But at this point, we wanted to be very conservative.
So you don't have an image? You never showed an image of maximum entropy?
I did actually. There was one of these that
Oh,
showed.
I see.
There
Okay.
were a couple of them that showed a much tighter
okay.
ring.
Okay.
And,
Interesting.
we
Yeah.
think that can actually
Would be real.
that's probably real.
Okay. If there are no other questions, okay.
Can I
You
do
have
another
one
one?
more. Okay. Yeah. Go ahead.
So with all of these different elements around the world, is the only issue in getting them to play nice with each other timing, or are there other nuances? All of these very different instruments.
Weather. Weather.
Oh, the politics. Well, the weather. Probably politics is the biggest part. I mean, getting everybody to work together has been a lot of work. He says, looking down and digging his toe into the ground. Thankfully, we had such a good science case. Everybody was really bound by a common science vision. But we had differences in the collaboration, I'll say that. I think it's because we had this creative tension where everybody worked together, usually in a non-adversarial way, in a constructive way, that carried us through. You want to create a culture in which everyone feels listened to. You want to create a culture in which everyone feels they're contributing. And you want to create a culture in which everyone feels they can raise objections without being vilified. And that is a difficult task. I think we succeeded in large measure. We're not perfect, but I think we considered in large measure, and that contributed to the robustness of our results.
Okay. With this note, let's thank the speaker again.